Hey guys, so today we're going to go over background 3 resistor combinations. The first thing to cover is resistors in series. So if we have a set of resistors in series, and I'll name them R1, R2, R3, and this can be like in a circuit or something. This setup is equivalent to having one resistor with its resistance equal to the sum of their resistances. That's pretty straightforward. Now, if we have resistors in parallel, which looks like this, and this is R1, this is equivalent to one resistor where the inverse of its resistance is equal to the sum of the inverses of the other resistances. And if you have more resistors, this just adds on, so we'd have like and it just continues to go on. This equation for parallel resistors works fine, but it is easier to use the reciprocal of both sides for R equals 1 over the sum of the other resistors. Or, I prefer this version. I think it's a little bit cleaner to work with, but everyone has their own preference. So when we have resistors in series, let's say we have a current flowing through these, I1, I2, I3. It turns out that they all have the same current, so I1 equals I2 equals I3. This is because if you have, it's like water flowing in a pipe, you know? If you have water flowing, it can't suddenly stop flowing, or you'll get like a really big buildup right there. The only thing is that can't happen with electrons because the electrons will all repel each other, so you can't just get like a whole buildup of electrons, it'll just explode. So yeah, the current is the same through all of them. Then the voltage is not the same across each one though. So the voltage 1 time is proportional to R1. So since they all have the same current, right, I1 equals I2 equals I3, then the voltages across them in series is proportional to their resistances. That's just straight out of these equations. For resistors in parallel, you can see right here, this set of wires all over here is one equipotential surface, and this set of wires all over there is another equipotential surface. So the voltage between those equipotential surfaces is the same for all the resistors. So the voltage across each resistor is the same. So you have V1 equals V2 equals V3. And then the current is not the same for all resistors. So we have I1 equals V1 over R1, I2 equals V2 over R2, I3 equals V3 over R3. And so they all have the same voltage, but if their resistances are different, then the currents will also be different. That's pretty much it for parallel and series. So now we'll go with an example of how to solve a circuit using these resistor combinations. So this is a monster circuit, but I'll draw it real quick. Okay, so I finished drawing this monster circuit. Um, you'll see a couple of the connections, or I guess just the one connection, I drew a little bit differently right here. That's just they're the same both ways. It's just because I thought it was easier to draw it the way I drew it. But yeah, it's the same either way because this is all one equipotential surface no matter what, and this is all one equipotential surface no matter what. So however you would hook up the circuit in real life on a breadboard, whatever, these would both end up being the same. So first thing I'm going to do is combine all these resistors that are in parallel. So the 4.7k and the 200 ohms will be, well, they will combine to 191.837, and then the other parallel combination over here, that one will come out to and make sure you notice whether or not it has a K or not in front of the ohm symbol, or else you can end up with the wrong answer. So these are those equivalent resistances, so I'll redraw the circuit with those instead. Okay, so now the circuit is redrawn, and now we have a bunch of resistors in series. So I will go ahead and combine those using the equation to combine resistors in series. And okay, and now we are down to a simple circuit. So the current through this simple circuit we can now find using Ohm's law. I equals V over R, and that gives us 1.161 milliamps. Okay, so now that we have that, we can upgrade our circuit up one level. Okay, now we know the current across each resistor is 1.161 milliamps. So now we can calculate the voltage across each resistor using Ohm's law. So for this one we have V equals IR equals and then the 10,000 ohm one we get so I used Ohm's law on every single one of these using, so V equals IR, since we know the current through the circuit, we know the current through here, and that is the same current through all of these. So we used Ohm's law to calculate the voltage across all of these. Now we will upgrade one more level. Back to the original circuit. Now that I've redrawn the circuit with all the resistances and voltages, then I will use Ohm's law again to get the current through each little through each resistor. The only thing is, we already know the current through these, because that is the same as the current above, right? We knew the current from here, and that carries to there, and it'll carry to here again. So we already know those currents. We really have to calculate the current through each of the resistors that we're splitting up right now into parallel combinations. So to do that, we just use Ohm's law again. So we use I equals V over R, and then what we calculate is I hope that concludes how to solve this problem. In summary, what we do is we start with a crazy circuit, and then we shrink it down. We shrink down the parallels, we shrink down the series until it's a simple circuit. You just keep shrinking until you get a simple circuit. Then you use Ohm's law to find the current, and then you split up by one level, and then use Ohm's law everywhere you can. Then you split up one level and use Ohm's law everywhere you can. If you have to split more, then you split up one level and use Ohm's law everywhere you can. But that's the process that you use for every time you get one of these problems. You just split it down, shrink it down all the way into its most simple circuit, then split up one level, use Ohm's law everywhere, split up one level, use Ohm's law everywhere, and you'll be done. I hope that was helpful. Yeah.